Good afternoon. It's my pleasure to be here. I'll be presenting our work on behalf of my student, Marzana Mahmud, who couldn't be here today. And I'm going to present to you a low-power gas sensor based on the CMUT technology. And I would like to acknowledge funding from NSF, which enabled this work. So we are actually performing this work as part of our NSF-funded Nano Systems Engineering Research Center for Advanced Self-Powered Systems of Integrated Sensors and Technologies. So that's a mouthful, but in short we call it ASSIST nicely. And the idea here is to make self-powered sensors that can monitor the physiological variables as well as the environmental variables and can correlate in a personal setting for many different people. So the key components of this research center are, of course, we developed the low-power sensors for correlated sensing. At the same time, we work on energy harvesting and storage technologies, and also fundamental technologies that would make low-power nanoelectronics for the next generation possible. At the same time, we work on low-power circuit design, and we bring all these components together. And there's a strong integration component of this research, and then we basically showcase these developed technologies in various different test beds. So for the sensors work, the challenges are achieving low power consumption, having high specificity, especially today I'm going to present to you about gas sensors, and also bring these sensors into a wearable form factor, and have robust, reliable, repeatable measurements using these sensors. So if you look at, in general, what we are trying to sense in our platforms, in our sensing platforms, first of all, we have the gas and the particulate matter sensing. You see that here on this side, that's our environmental sensing. And on top of that, we have all these other physiological sensors, biochemical sensing, particularly for sensing cortisol, bioelectrical sensing for EKG recording and also monitoring hydration levels, lung sounds, that's mainly to monitor asthma conditions, and also a custom pulse oximeter that runs at low power, and that's for the heart rate basically. But in today's presentation, my focus will be on the polymer-coated MEMS technologies, and in particular, we use the Capacitive Micromachined Ultrasonic transducers as a resonant gas sensor with proper functionalization. So in today's talk, first I'll give a brief introduction to CMUT, and then I will talk about the fabrication methods that we developed for the transducer technology that we use. I will go into some details of the oscillator design that we used in this work, and then present to you the preliminary chemical test results that we obtained recently. The Capacitive Micromachined Ultrasonic transducer is simply a vibrating thin plate that is electrostatically actuated. And here what you see is the basic building block of this transducer. And you can imagine that you can put many of these little drum heads electrically in parallel, and then you can make transducers in arbitrary shapes and arbitrary forms. You can make them into arrays, and that basically gives you a really nice broad sensing area, right? That's one of the advantages of this technology. And compared to other mechanical resonators like the fixed beams or cantilevers, you would see that here we have a vacuum backing, which helps with the quality factor, and that's an advantage in the sensing applications. As I mentioned, these transducers are made by connecting many different cells, and that improves the robustness. And for, of course, multi-dimensional sensing, you need a number of elements that can be functionalized with different polymers in this case, and this technology also is very suitable for that. So previously actually this technology has been used for chemical sensing applications. However, in those demonstrations, the main focus was on really pushing the sensitivity, because it was mainly for defense applications, trying to detect the DMMP primarily, which is a simulant of sarin gas. And in that case, the operating frequencies were much higher, around 50 megahertz, and ppt-level sensitivities and detection limits have been demonstrated, but with pretty high power consumption, which is in the multi-tens of milliwatt range. So different than the previous work, what we focus on in the current work is to play these different trade-offs in this very versatile and very flexible device structure, and basically develop low power sensors that are suitable for the general vision that I described, which are wearable low power sensors, all self-powered for environmental monitoring at a personal level. And particularly with this kind of sensor, we are focusing on detecting volatile organic compounds, which is a major pollutant, especially in the indoor environments. And what we are basically doing is we bring down the oscillation frequencies from tens of megahertz to 5 megahertz level, and that enables us to trade off the sensitivity with these low power requirements, and that's more than adequate because in these kind of settings, the required sensitivities are really in the high ppb to ppm level for this kind of analyze. So let me give you a brief introduction to the fabrication technology that we developed to make CMUT. We start with a borosilicate glass wafer. After standard cleaning and photoresist spinning, we use our first mask to define the active region of this transducer, and we use wet etching to define the cavities of the device. And without basically removing that photoresist, we go ahead and evaporate the metal electrodes and lift off. So with one lithographic step, basically we have our bottom electrode all defined. And then the next step in the process is to use a silicon on insulator wafer, which would give us the vibrating plate structure. And for the electrical insulation between the bottom and top electrode, in case of contact, we use a thin silicon nitride layer, which is shown. Let me use the pointer here. So this is the thin silicon nitride layer that we deposited on the device layer of the SOI. And after bonding this SOI using anodic bonding, which is really a nice, convenient way to perform this bonding operation, because it can be performed at low temperatures, and it can also tolerate fairly high surface roughness. So that's the major advantage of using anodic bonding compared to other bonding methods like fusion bonding, which are performed at very high temperatures. Then the next step is to remove the handle layer and also the box layer of this SOI. So we end up with this basic structure where we have the vibrating plate and the bottom electrode. So this can be electrostatically actuated to have the vibration. But there's a problem here. I mentioned to you about the vacuum backing, but what you see in the surface profilometer measurement, these plates are buckled up. This is actually something expected because one of the byproducts of anodic bonding is the oxygen comes to the surface, and if you're trying to implement this kind of a structure, it fills in the gap, and in this case, we actually have these pressurized cavities. So the next step would be then to open up this cavity and remove that gas, and in the next step, we seal that gap in a vacuum environment using a silicon nitride deposition. And the next step is to open up the contact pads, and at the same time, we also remove the silicon nitride on top of the silicon plate, and we only leave it to at places where we want to have the sealing. And at this step, if we go back and look at the surface profile, we actually verify that we have the vacuum backing, and the device is ready for the final use. So just to bring this again into attention, we had this pressurized cavities after the bonding, but we evacuated the gas and resealed, and this is what we expected. Basically, our FEM simulations also verify that this is what you should get when you have vacuum on one side and the atmospheric pressure on the other side. So at this point, this is the final device. This was the structure that we would like to implement, and this is the final SEM showing that structure. Here you have the top metal, the thin silicon plate, and the silicon nitride insulation layer, the bottom electrode, and the cavity. And with this process, we also showed that we can get pretty good bottom electrode roughness, about 2 nanometers RMS. And on the bonding surface, we have 0.7 nanometer RMS, which is more than enough for anodic bonding. And then now we are ready for actually using these devices for gas sensing. And the first thing we do is we characterize their electrical input impedance. And in this case, you see a nice high Q resonance, about 200, Q of 200. And we also fit to this measurement standard resonator model so that we can use that in our oscillator design. So with this, we designed this standard Colpitts oscillator, which is really one of the key things in developing this low power sensor, because with this kind of a single stage tuned oscillator, we were able to get the power down to 77 microwatts with this circuit, and this is all discrete implementation when we power cycle at 10% level. So in this case, in this work, what we present is a resonator that is resonating around 4.5 megahertz. And the oscillator here in this case just tracks the oscillation frequency, the resonance frequency of the resonator. And what we do is we operate this device near the parallel resonance frequency, which gives an advantage also in the high quality factor. The next step is to functionalize this resonator with a polymer and use it for gas sensing applications. So before I present to you the gas sensing results, let me also give you an idea about the performance of this oscillator. If you look at this Allen deviation with 10 millisecond gate time, we measured an Allen deviation of 1 hertz. If you consider the 3 sigma frequency noise, then that means we can see changes in the oscillator frequency about in about 3 hertz or so when we use this averaging time of 10 milliseconds. Another important result that I would like to share with you is this here. This shows what happens when you when you power on the sensor. It can basically start oscillating in about half a millisecond or so. So this is an advantage because in the kind of application that I described, you do not really want to sense continuously, right? Because this will be with the person continuously, but you can turn it on and off on demand, and you can just take measurements whenever you want, and that will keep the average power consumption low. So having this kind of a quick startup reduces the overhead of turning the device on and off, and you can power cycle and reduce the power with this kind of oscillator. So here's our gas testing setup. What we use is a calibration wafer generator that works with a clean air generator, and we can basically generate trace amounts of different VOCs, and then we can pass that through the device, which is shown here. If you take a closer look at it, you will see the resonator here with the discrete circuitry next to it, and there's a little container built on that, which is made of acrylic glass. And we have the inlet and the outlet, and we can basically turn the flow on and off, and we can test the sensitivity of this gas sensor. And also to take a closer look at the device itself, here the active device is shown in this rectangular region, which is our resonator that is composed of hundreds of these resonating cells that I described to you in the beginning. So just to show you that, okay, this works as a gas sensor, here we tried toluene, and that's one of the target analytes, as I mentioned to you, because it's a VOC. And what we did is we functionalized this device using PIB, and then used this in that chamber, and we changed the concentration of the toluene and showed that we basically can achieve about 270 hertz per ppm kind of sensitivity, and we tested this device in the 10 to 20 ppm range of toluene concentration. So just to summarize, today I described a novel fabrication method for CMUTs based on anodic bonding, which has various advantages in terms of the simplicity of the process and also the performance of the devices. We fabricated fully functional, high-quality factor CMUTs using this process, and we demonstrated using these devices that we can achieve toluene sensing at the sensitivity levels of 270 Hz per ppm, and the frequency noise of this oscillator was at the 3 Hz level, which basically gives you a limit of detection in the low ppbs. So this is more than enough for the application that we are targeting, and we were also able to demonstrate that this result can be achieved while consuming low power. Our initial target was to stay below 100 microwatt, so that we are in agreement with the power that we can generate from our energy harvesting devices. And we were also able to achieve that with 10% power cycling. And our current concentration is basically building multiple of these devices as an array on one chip, and use multiple channels with different functionalization layers to show a more selective sensor for VOC detection. So at this point, I would like to stop, and I'll be happy to take any questions you have.